Greetings, my fellow geothermal students. Professor Jonathan Bowe here to get going with some plate boundaries today. Plate tectonics. That's where all the geothermal is located, or not all, but that's where it's closest to the surface. So let's take a look at some plate tectonics in our lecture on plate boundaries.
I'm sure we can go to ground with this one.
To understand more about plate tectonics and continental drift, we have to look deep inside the Earth. The Earth's interior consists of several different layers. The inner core, which is believed to be solid iron and which is very hot. The outer core, which is believed to consist of rocky material so hot and under such great pressure that it is in a liquid state. The mantle, which is not as hot as the outer core and not as liquid. The mantle's outermost portion is solid. This is the solid outer portion of the mantle. Above this is the outermost layer of the Earth, the crust. Together, the crust and solid outer portion of the mantle form the Earth's outer shell. They are referred to as the lithosphere. It's not always easy to see the Earth's crust. It's covered by vegetation and the oceans. But if you could drain the Earth's oceans and strip away our planet's vegetation, the Earth might look something like this. Now we can see the Earth's hard outer shell. And if you look closely, you can also see the shell is cracked. The red glowing lines mark the places where the Earth's shell is cracked into tectonic plates. Each plate carries a continent or an ocean basin, or sometimes both. The plates are moving at an average rate of 1 to 2 inches a year in a variety of directions, carrying continents and ocean basins with them. Here's why the plates are moving. Scientists believe material in the mantle is circulating much as it is doing here. The movement may be caused by heat within the mantle. You can get an idea of how heat can cause a circulating movement by watching rice as it boils. What you see happening within this beaker is similar to what's happening within the Earth's mantle. As mantle material moves, perhaps only inches a year, it causes the plates above it to move as well. In some places, plates are moving in opposite directions. They are moving apart. The area where two plates are moving apart is called a divergent boundary. In other places, plates are colliding. The area where two plates are colliding is called a convergent boundary. And in other places, plates slide past each other. This area is called a transform boundary. This is a cross-section of a divergent boundary, the mid-ocean ridge, located beneath the Atlantic Ocean. The North American plate is on the left, and the Eurasian plate is on the right. Scientists believe that as the plates move apart, mantle material called magma rises to fill the gap. Magma is the name we give lava before it erupts from volcanoes, as it is doing here. The magma cools and hardens on the ocean floor, adding new crust to old. And as the seafloor spreads, North America moves farther away from Asia. The highlighted area on this globe shows where magma is surfacing between plate boundaries beneath the oceans, creating a mid-ocean ridge that circles the Earth. The ocean floor spreads in one direction on one side of the ridge and in the opposite direction on the other. The mid-ocean ridge is where plate material is created. And this is where plate material is destroyed, a convergent boundary. In this cross-section, the plate on the right is carrying an ocean basin and is moving in this direction. The plate on the left is carrying a continent and is moving in the opposite direction. The plate carrying the ocean basin is heavier and is diving beneath the plate carrying the continent. The leading edge of the diving plate is consumed back into the Earth's mantle. When one plate dives beneath another, it is called subduction, and the area where it occurs is called a subduction zone. Subduction may resemble what is happening on this lava lake as sections of hardened crust dive beneath other sections. The highlighted areas on this globe mark convergent boundaries. Subduction is occurring at most of them. These are the areas where plate material is destroyed. Here again are divergent boundaries, where plate material.
So you notice here how the shapes, the actual, where it's subduction zones along these coasts here, see these are divergent. This is where the replenishment is happening out in the middle of the ocean. But you see how it reflects the shape of the coastline here. Kind of cool, huh?
Material is being created. Again, most of them are beneath the oceans, creating a mid-ocean ridge that circles the globe.
Except for the Pacific Ring of Fire. Here's a National Geographic on the colliding continents. This is more of an historic view, but we're not going to look at the whole thing here in our lecture, but if you would like, it's in your central column of your course. You can take a look at it. That's your important things we need for the quiz are
Planet Earth, hundreds of millions of years in the future. Intergalactic explorers return to their home planet in search of signs of ancient civilizations. They find a planet that has changed beyond recognition. Gone are the familiar continents that we know today. Instead, they find a giant landmass with huge mountain ranges, massive frozen snowfields, and glaciers. The once thriving metropolis they seek has disappeared. A few broken remnants are all that remain, crushed and buried beneath tons of rock. Could this be a future vision of Earth? Naked Science asks, what forces could create such a bleak and barren world? And investigates how the awesome power of colliding continents shapes and reshapes our planet in an endless cycle of construction and destruction. Our world, the Earth. From space, it's easy to see the distinctive pattern of land that makes up the continents: North America, South America, Africa, Antarctica, Europe, Asia, and Australia. Giant landmasses separated by oceans that stabilize the environment with hospitable weather patterns, suitable for civilization and cities to evolve and prosper. Now imagine our planet ravaged by storm force winds, subjected to extremes of temperature, giant freezes, heat waves, and droughts. A world where cities are crushed and destroyed, where Africa tramples New York underfoot, and London freezes at the North Pole,
The geological future of New York is going to be rather traumatic. North America and Europe are going to collide with one another.
The world as we know it will be unrecognizable. This is not a portrait of the Earth after a devastating global disaster. This is how nature will shape our planet many millions of years in the future. This incredible remodeling is just part of a natural cycle that has shaped the Earth for the last 4 billion years, and will continue to do so until the sun finally destroys its surface once and for all. Today, our continents may seem solid, safe, and forever fixed in place, but they are none of those things. These great landmasses are constantly on the move. Speed up the last few billion years, and one can see the continents sailing across the globe. Powerful forces deep within the planet rip the continents apart and then smash them together in an ever-changing cycle of death and rebirth. Oceans disappear, mountains crumble, and rise again. Landmasses form and reform. Colliding continents are the mightiest force on Earth.
When we look at the history of planet Earth, we see that it is full of change. Change is part of nature, and this change continues today and will continue into the future.
To understand how the continents shape our world, we must first travel back in time to the very birth of the Earth. 4.5 billion years ago, the Earth is created from the debris left over from the formation of the Sun.
Big Bang Theory. Not necessarily.
Dust and debris collide and clump together. Samples to date the age of the granite.
We're drilling these little...
Minerals can break down and reform into new rocks. Scientists look for an ingredient of rock that is tough enough to withstand the test of time. The answer is zircon, a crystal that is made inside molten rock as it solidifies. Even if the rock is destroyed, the zircons are durable enough to survive.
Zircon is an incredibly interesting mineral, and it incorporates uranium and excludes lead, and that sets us up to have basically nature's time capsule.
To illustrate this process, imagine that this hourglass is a newly formed zircon crystal. Sand in the top represents uranium. The sand in the bottom represents lead. Over millions of years, the uranium in the zircon turns into lead. Measuring the relative proportions of sand in the top and bottom of the glass reveals how much time has passed. Uranium's relentless decay into lead gives us a natural clock. Using this technique, geologists date this granite at 3.5 billion years old. This makes it some of the oldest rock on the planet. These rocks make up a major part of what is known as the Kopval Craton. A craton is an ancient raft of rock, light enough to float on the mantle, and around which a continent will grow. Ancient cratons have also been found in the heart of the Australian and North American continents. The craton here in Kopval in South Africa stretches for 463,000 square miles. It's almost twice the size of Texas. Without granite, the craton and modern continental crust wouldn't exist. Granite forms when minerals in the crust melt, then react with water, cool, and crystallize. Because it is made of lighter minerals, granite is less dense than other rock in the mantle, so it floats on the surface and mixes with other rocks to form rafts of land. The Kopval Craton is not totally built from granite. The oldest rocks here are these amazing pillow lavas exposed along the Komati River. 3.5 billion years ago, they form under the sea as lava emerges from an underwater volcanic vent. Upon contact with water, the lava immediately gains a solid crust, which then cracks and oozes additional large blobs called pillows.
These rocks are amongst the oldest that we know. It's basically identical to pillow lavas that we see on a recent ocean floor or in settings like Hawaii.
The Komati pillow lavas begin their life on the ocean floor, but are pushed up out of the sea to form part of a continent. But where did the granite come from? To create it, you need the right mix of minerals. A new theory suggests that life itself may have provided the missing ingredients. It may sound like an outlandish idea, but there's some evidence that living organisms that use photosynthesis appeared around the same time that the continents began to grow, 3.8 billion years ago. Scientists suggest that early organisms, microbes, helped speed up the breakdown of rock emerging at the Earth's crust. Over hundreds of thousands of years, this rock breaks down into new minerals, which sink back into the mantle. Deep below the surface, they heat up and form granitic magma. The magma rises into the protocontinent, freezes, and forms huge solid rafts of granite. Now stabilized, the craton begins to grow, forming new baby continents. But cratons are not the only factors at work. More powerful forces are building up deep within the planet. Forces that have the power to rip apart landmasses and smash them together, changing the face of the planet forever. Four and a half billion years ago, the Earth forms. For many years, it is bombarded by asteroids and meteors. Slowly, the molten planet cools, and small landmasses form around cratons of granite rock. Massive forces from deep within the planet rip apart and smash these small protocontinents together as they grow into the large landmasses we see today. The surface of the Earth, the crust, is made up of a giant jigsaw of interlocking pieces called tectonic plates. The separate plates themselves sit on the mantle, the layer between the crust and the Earth's core. Although the mantle is made of rock, the heat and pressure deep down mean it's flexible enough to allow the plates above to move up to several inches a year. Evidence for the theory of continental drift was first proposed in 1912 by German scientist Alfred Wegener. He noticed that identical fossils were discovered oceans away from each other. Paleontologist Professor Mark McMenamin of Mount Holyoke College in Massachusetts is an expert in fossil records.
Wegener noted that a freshwater organism cannot cross a salty sea. And so if you find the fossils of a freshwater organism or a land creature on two continents that are now greatly separated by distance, they must once have been closer together.
Mm-hmm. So let's move this on up into the actual descriptive.
Much of the heat is left over from the collisions and massive bombardment during the early days of the Earth. The rest comes from radioactive decay of heavy elements in the core. Heat escaping from the core creates convection currents in the next layer
Radioactive decay in the core of the Earth, or isotopic degradation.
of the Earth, the mantle. The process is like a lava lamp, where heat from the bulb at the bottom creates convection currents in the oil, pushing the synthetic lava upward. The heat melts part of the mantle and sends plumes of magma, molten rock, rising to the surface. It rises between cracks in the plates, creating new rock that pushes the plates apart.
Divergent.
I think that plate tectonics is virtually inescapable on this planet. It's an exceedingly efficient way to cool the interior of the Earth.
This formation of new rock splits apart and separates the plates and the continents sitting on them. Today, the majority of this new rock forms under the sea, creating vast interconnected volcanic mountain ranges that extend through all the major oceans of the world. One range can clearly be seen at the bottom of the Atlantic Ocean along the Mid-Atlantic Ridge. It stretches more than 12,000 miles from the subantarctic to the Arctic. It comes to the surface in a few places. Iceland was created from volcanic lava bubbling up at the junction between the North American and Eurasian plates. It's one of the few places on Earth that one can actually see continents being pushed apart.
We are watching here geological structures that you cannot really watch anywhere else. It's like a big textbook of geology. This is where the Earth's crust is being made.
Paul Einarsson, professor of geophysics at the University of Iceland, monitors the mid-ocean ridge where the continental plates are splitting apart. The ridge in Iceland is almost 3 miles wide. On one side is the North American plate, on the other side, the Eurasian plate. The rift here grows as new rock forms at its center, pushing North America and Europe away from each other. The Atlantic Ocean widens, and the two continents drift apart. Eventually, the Atlantic could become as big as the Pacific. To measure how fast they're splitting, Einarsson takes global positioning system readings at specific points along the plate margin.
We put the antenna right on top of the point, and then we can calculate the exact position of this point in the world.
Show that the two continents are drifting apart by around an inch a year. So by the end of the century, Europe and America will be almost 8 feet further apart. The movement in Iceland is typical of the processes shaping the continents since their birth 4.4 billion years ago. It's part of the great cycle of the Earth's continents. The new crust, created at the mid-ocean ridge, moves away, cools, and eventually sinks back into the Earth. When the first proto-continents formed, there were several interconnecting tectonic plates, constantly bumping and grinding against each other, pushing the new land over the planet. Today, the Earth has over a dozen plates, some colliding together, some moving apart. They are powerful enough to move a continent the size of North America over 3,000 miles in 200 million years. That's 15 miles every million years. The Earth, 3.4 billion years ago, and plate tectonics pushes the proto-continents together. They combine to form ever larger tracts of land. Scientists suggest that cratons combine with other cratons to form a supercontinent, a huge continuous stretch of land. It's called Valbara. Scientists are unsure of its exact shape or size, as only a few pieces, like the craton in South Africa, still remain. But Valbara's days are numbered. A rising plume of heat is growing beneath it. It's about to rip the world's first supercontinent into pieces. $2.7 billion years ago, Valbara, the world's first supercontinent, still dominates the planet. But plate tectonics, powered by heat from the Earth's core, is about to split it apart. Rock is a good insulator. When a continent gets very large, the rock traps heat beneath it. As it gets hotter and hotter, a plume of superheated magma builds up beneath the giant continental mass. The temperature continues to rise, and pressure in the mantle increases. Eventually, the crust can no longer contain the pressure, and the hot lava breaks through, ripping the land apart.
Sound like Yellowstone? Could be what's happening in Yellowstone Park. Well, that's the actual mechanics, the plume's coming up underneath the center of the continent here in the North American continent, but it's not a supercontinent, but it's one of the larger land masses on the globe.
You can see this process happening today in Africa. Heat from the Earth's core is ripping the continent apart. A giant rift valley runs from the Red Sea down to Mozambique. Giant cracks are opening up in the land.
The Rift Valley, like we talked about, the Snake River Rift that comes, it's a transverse rift that runs from the western coast out in Oregon back in through Idaho and up into Yellowstone. And the Yellowstone volcano is the current opening in that magma plume.
Volcanoes, like Kilimanjaro, mark spots where molten rock have risen to the surface in the past. In 10 million years, the eastern half of the continent will have split away. The molten lava trapped beneath the giant supercontinent of Valbara eventually smashes through the surface rock. The continent ruptures into several smaller pieces. These bits of land sail across the Earth. But nobody knows what happens to them or what the planet looks like at this time. The Earth is entering the Dark Ages. It is over 2.5 billion years since it... Well, no one knows exactly what it looked like, but at its heart is an area that will eventually become North America. 350 million years later, the cycle of annihilation and creation starts again as the buildup of heat beneath the surface of the Earth tears Rodinia apart. When Rodinia splits, it forms several smaller continents that for millions of years drift apart and then drift back together again to form Gondwana, a supercontinent in the southern hemisphere. Eventually, after several hundred million years, Gondwana slowly splits apart. Plate tectonics push the land back together.
It's interesting that the Great Lakes is such a prominent feature here. Well, that's not, no. It's all theoretical though, huh?
To create the world's last supercontinent. It's a huge landmass known as Pangaea. All the continents we know today are here, joined together. Geologists are able to plot the continent's relative positions because 350 million years ago, there are numerous species on Earth, each living in distinct regions.
This specimen that I have right here is the first trilobite that was ever described from what is now the United States. It is...
So there's their geological proof or paleontology.
To warmer climes. The positions of our continents are becoming familiar, although their distinguishable features are not. The world's vast mountain ranges, the Alps and Himalayas, and its great valleys, like the Grand Canyon, are yet to form. They will emerge out of one of the biggest battles in nature, the battle between colliding continents. Earth, 100 million years ago. The continental map of the modern world is gradually becoming recognizable. But a battle is still raging between the continents that will change the face of our world forever and create some of the most extraordinary geological features on the planet. As the continents move slowly across the Earth, crust and rock is dragged back down into the Earth at subduction zones between the tectonic plates.
Subduction zones. So we had the divergent generation in the center of the Earth, or in the center of the oceans, where the crusts are replenished, and the oceanic crusts are heavier than the continental crusts. And then we have the replenished crust that comes over, gets up against the continental plate. The suboceanic plate is heavier, so it dives or subducts, goes under in this convergent coming together, divergent going apart.
But when continents collide at the plate junctions, sometimes there is a battle for supremacy. If neither plate will submit and drop down to be consumed by the mantle, then both the continents slowly smash and grind into each other. These pinch points of continental collision build mountains. The Alps are the largest mountain range in Europe. Higher than the Rockies, the Alps stretch from France in the west through Italy, Switzerland, and Austria to Slovenia in the east. Their formation is a direct result of a continental collision between Africa and Europe. The story of the Alps begins when the African plate breaks away from the South American plate. It starts moving toward Europe.
Without the plate movement, there wouldn't be any mountain on this planet.
So now we're getting into the meat of this. Is we've talked about divergent and convergent plate boundaries. So let's move forward here.
You're actually staying on top of Africa. For geologists, Africa stops in the Alps.
Over the next 100 million years, the continents continue to smash together. New mountain ranges start forming around the globe. The largest, the Himalayas, form as the Indian plate charges northward toward the Eurasian plate. It moves at 2 inches per year, lining up a head-on collision. The movement of the Indian plate leads to a clash between 2 giant continents and creates some of the highest structures ever to exist on Earth. The incredible power of continental drift not only builds mountains, it also sculpts one of the world's most recognizable landmarks, the Grand Canyon in Arizona.
The Grand Canyon is a great scar on the surface of the Earth.
Geologist Ron Blakey has been studying the canyon for over 30 years.
It's just a wonderful place to come face to face with planet Earth.
The Grand Canyon is 277 miles long and up to 18 miles wide. At its deepest, it stretches down for over a mile. The gorge exposes the interior of the North American continent. It's like looking through the pages of a book. Each layer tells a story about the past.
One of the really neat things about Grand Canyon is as we go up the walls of the Grand Canyon, it's like going through a time machine.
And there you see a divergent feature, huh?
1 million years to form a vast plateau far above sea level. It stays that way for millions of years until it is transformed by water erosion. Time, water flowing freely between the Pacific and Atlantic Oceans still separates North and South America. Over many millions of years, the Pacific plate begins sliding under the Caribbean plate. The pressure causes underwater volcanoes to erupt. Some explode with such ferocity that they create a range of small islands between North and South America.
So we'll see that at the convergent tectonic interfaces or plate boundaries, we see more aggressive volcanic eruptions. Volcanoes are more abrupt, tend to be taller in nature, and more concentrated, whereas in the divergent boundaries we tend to see longer term, less violent volcanic eruptions, like in Iceland, where it's a lot of geothermal activity that they actually harvest, and we'll look at that too in our course.
Over the next 17 million years, ocean currents deposit sediment in gaps between these new islands. Gradually, the sediment builds up and compresses in South America.
So now another resource for you that you can refer to, very handy for your quiz taking, is the tectonic plate boundaries here. It's a Wikipedia. And take a look at the plate tectonics. You can really go into detail with these. Diving forces of a plate motion, mantle dynamics, diving forces, which would be subduction, correct? Floating continents, paleomagnetism and seismicity zones. We're going to talk about that as far as earthquakes, seismicity, indicating that there's interaction and probably heat closer to the surface. But with new drilling techniques, you can get the heat you need pretty much. And new science as far as compressors, magnetically levitated bearings that allow us to get 4 units out for every unit put into as far as work is concerned. So we get some pretty efficient compressors. Key principles you see here, and if you click on these little guys, and it'll take you to that embedded. You can take it real quick, you can find the information that you need here. Let's take a look now at our plate boundaries. Types of plate boundaries. We have a transformal boundary. It's conservative. Occur where 2 lithospheric plates slide, or perhaps more accurately grind past each other. See the information here, a transform boundary. We have the divergent boundary. Divergent boundaries occur where 2 plates slide apart from each other at zones of ocean-to-ocean rifting. Divergent boundaries formed by seafloor spreading in general, although there is a divergent continental boundary up in Iceland. So now, convergent boundaries are destructive. Divergent boundaries are constructive. So where it's coming apart, it's building new materials coming up. Where it's convergent, you see it here, it's convergent boundary, it's diving, and it's destructive. And the volcanic eruptions associated with divergent boundaries are usually more gentle in nature and longer duration, whereas a convergent boundary, the volcanic eruptions are more aggressive, more violent, and shorter duration. And driving forces of the plate motion, we talked about the mantle, dissipation of heat from the mantle, and that's the convective cycles that we can see here, where these are the replenishment zones. If you look over here, you can follow my little hand over to the right hand side of the page. You can see the little, or the central area here. So if you can make out the North American continent here somewhat, ring of fire, Pacific ring of fire over this way, and then we've got the Atlantic trench right here that they talked about, and these are replenishment zones, so they're diverging, and then the blue areas along the edge here are destructive or converging. So that kind of gives you a nice source for your basic plate boundaries. Right here they are. Good luck on the quiz. The quiz is open for you now, and let's make sure that you do get into your smart geothermal. So please open up your textbook and read through chapters 4 and 5. There will be a quiz on how to harvest Earth's free energy. And that's going to be more local. This is Jonathan Bowe signing off for now. Good luck on the quiz, guys.